Hello, and welcome to Python for Informatics. Right now we're going to cover Chapter 1. I'm Charles Severance from the University of Michigan, and I'm the author, and I'll be your lecturer for this online lecture of the first chapter of the book. This lecture and my slides and the book, as a matter of fact, are all open content, open materials. They're copyright Creative Commons attribution, and this video recording is also copyright Creative Commons attribution. It's important to be explicit about copyright, and so I say it right at the beginning. So computers basically want to be helpful. They are programmed. Matter of fact, this is a microprocessor. This is really just an electrical part. It's got wires and circuits inside of it, and somebody spent a lot of engineering time to make it so that these pins in the back take instructions from us, from operating systems, from the hard drive, from the memory. Instructions come into here and then results come out. It's really sort of a very programmable hand calculator, and it's our job to put instructions in. This thing, in a sense, is wired to be curious about what's next, right? It's like tell me what you want to do next. What do you want to do next? What do you want to do next? And after that, what do you want to do next? And it just happens to do that a billion or so times a second. And so that's sort of the low-level piece. But you can also think, if you have like a PDA, something like this, all of the buttons on here are some kind of, what's next, right? Each of those is sort of something begging for my attention. Some application developer who's built a really cool application and says, please use me, please click me. I am sort of nothing without you. We humans are the things that sort of cause computers to start doing something. And this will sit here happily until I've caused it to do something. Now, whoa, hope it's still okay. Yeah, seems to be fine. Seems to be fine. Takes a licking and keeps on ticking. So these anyone can use, right? They say even animals can use a Macintosh smartphone. And so you don't have to be a programmer. But to get this to do what you want, you need to learn a different language. And we need to learn the language of the instructions to tell it what to do. So that's what we're going to do. We're going to learn how to talk to this. Yo! Because it's asking us a question, we have to give the answer. So what's a programmer? A programmer is somebody who writes a program, which is a script or a set of instructions that tell one of these kinds of things what it is that they're supposed to do. And sometimes you're running a program like Moodle, an open source learning management system, or Sakai, another open source learning management system. And sometimes you'll even get paid to do that, right? Sometimes you do it for free, sometimes you get paid. Sometimes you write things for yourself. But if you think about it, all these applications on my iPhone, somebody's making some money off of these. They may not be able to quit their job, but a surprising number have been able to quit their job or start small companies. Maybe not gigantic companies, but small companies. So these people that can put applications inside of our computers are programmers, because they understand the way that we talk to these computers. And part of what I'm going to try to do is to get you to move from the mindset of the end user who thinks of this as something just to click on, to the mindset of the programmer who's kind of on the inside trying to get out to you. So that's, as we sort of move from user to programmer, we move from outside to inside, and we think of the world out there. It's like, what are they going to push? What button are they going to push? So here's kind of a picture of that. So on the outside, we're users. We click on buttons, we click on websites, we click on buttons on our phones, etc., etc. But what's really going on inside of all that is there's a computer with a bunch of hardware inside of that. And it has inside of it data, networks, other information, and software is what makes all that make sense. And so part of what I want you to do is I want you to stop thinking about how to use these things from the outside, and we move to becoming a programmer. We're someone on the inside. We're with the CPU. We're with the memory. We are with the network connection. We are doing things on behalf of the user and presenting them back up to the user. So why be a programmer? Now, this class is specifically not trying to turn you into a professional programmer, even though I'd be very proud if after 5, 10 more classes you were a professional programmer. But that's not the purpose of this class. Sometimes you just want to get something done. You got an Excel spreadsheet at work and the data's not right. You got the data from somebody else and it's got like extra spaces where it shouldn't have it, or the missing fields or something. You got to do something to it that Excel can't do, and you're stuck like saying, "Oh, I want to mess with this data and put it in Excel so I can do my job, but it's a pain in the neck, and I have to sit and bring it into a text editor like Microsoft Word and go line by line and make all kinds of mistakes and clean the data up." You can write a program to do that, and that's the kind of programs we're going to do. Programs that serve our needs inside the computer, but to serve our needs. Professional programmers tend to build things for other people to use, right? They tend to build things that everyone else does, but we're going to build stuff primarily for ourselves. So, what is code? What is software? We use these words pretty much independently. A program. It's really a sequence of stored instructions. We learn the language that this talks, and then we will feed the instructions in, one at a time. It takes them one at a time. It gives us back a result. We give it a next one. Give it back, in, out, in, out. So it's really a sequence of stored instructions, but it's kind of more than that. It's sort of like our creativity. And if you've been using some of my software, like my MOOC software, I spent about a month writing all that stuff. And it's like, it's me. I mean, it's my vision of how cool stuff ought to work, right? And so it's more than just getting something done. It's also a sense of pride and a sense of accomplishment, especially if you're giving something that other people can make use of. It's really, I think it's very creative. And it's what attracted me to being a programmer in the first place, is that I could leverage the capabilities inside of here, and I could do things, the cool things, on behalf of the user. So, code, software, a program. So, let's get a non-technical example of this. So, I'll have you link out to the YouTube for this. This is the Macarena. The Macarena is a song that has with it a well-known dance that everyone seems to know or either get taught very quickly. So I'll stop and let you watch the Macarena and then come back. So welcome back. I hope you enjoyed that. In a sense, what we've got there is a program for human beings. And maybe you learned that at a club or something and they told you what to do next. Well, I can teach you how to do the Macarena by writing a simple program right now. So here's my Macarena. While the music plays, means you do it over and over and over again, to the beat. That's kind of like computers. They do things in a beat. They happen to have 3 billion beats a second, but as it were. So we're going to do this multiple times. So we have this whole group of instructions that we're going to do, right? Left hand out and up, right hand out and up, flip left hand to right shoulder, right hand to left shoulder, etc., etc. Now, this particular little program has a mistake in it. Actually, several. I want you to look and see if you can find the mistakes in the program. Okay, so here are the places that have the mistake, right? The mistake is right hand to the back of the head and left hand to right hit, not hip. Now, if you're in a bar and you take a ham and you hit somebody in the back of the head, that's not very nice when you're dancing to this song. These are what's called bugs. Now, a human reading this would say, oh, I think they meant to say hand here. But a computer is much more literal than people. We'll see a couple of exercises where we'll see that people can correct little mistakes like this, but computers, they cannot, right? So we have to fix these bugs, and we have to say right hand, and we have to say hip when we mean hip. So we have to be explicit. Computers do exactly what we say. They don't do what we mean to do. So let's clear that. Here's another example. Okay, see how this comes out. You're supposed to count the number of times the word the appears in this sentence. Count it. And the word the, how many times? Okay. It's your turn. Now here, this is not something humans are good at. I moved it around, I played a little music, I confused you, I put a picture of a clown car in the upper left-hand corner, etc., etc., etc. Now it turns out that computers, once we tell them what to do, are very good at concentration. It can easily go through 30 words and find the most common word, or 3 million words and find the most common word, and it'll never make a mistake. But we first have to give it a set of instructions. So I don't want you to learn this right now, but this is a Python program. Let's say that I wanted to let you count words in files. Okay? I say, hey, I know how to program Python. I'll send you an email and I'll send you this program. Just stick it into Python and it'll count words for you. Right? You got 1 million words, 1 million lines in a file. You want to find the most common word. And so here we go. So I will send you this file called words.py. I spend a little time. It's a friendly gift to you. And this is what I type in. Now I'll give you kind of an outline of what this is going to do. First thing it's going to do is open a file and read it. Then it's going to split the lines and files into words based on the spaces. Then it's going to run through and accumulate numbers. Like, you know, this word is 1, this word is 1. Oh, I saw that one again, so I turn that to 2. That's what this does. It's a loop. It goes round and round and round, one for each word. Then what we're going to do is we're going to write another loop that's going to figure out which is the most common word by looking through all those little histograms that we built up. And then it's going to print those things out at the very end. And this can certainly do Python words.py and read clown.txt and tell us that the word the occurs 7 times. But, you know, it can find out that a different thing has the word to and occurs 16 times. And it's just as fast. And it's so yeah, you have to learn a language and you have to tell it what to do. But once you do, it'll do it for 1 million or 1 billion words and be happily. And so you don't have to do menial work once you understand the way to instruct the computer to do menial work. So we always start all programming classes with hardware architecture. I don't think it's essential, so don't get too excited about it. It's a good use of terminology so we can have some words. I can say like CPU and you don't freak out, or memory, or RAM, or a disk drive, and you don't freak out. I don't want to turn you into a hardware nut. I just want you to kind of have a few words so we can talk about what's going on inside, because in a sense we're going to be writing programs to do stuff, both data, instructions, etc. So here's some hardware that I just bought a couple of weeks ago and I'm really in love with, and that is the Raspberry Pi. This is a single board computer. It's got storage on an SD card right there. That's the operating system and the data. And it's got the both a microprocessor and the memory is in here as well. And it hooks up with USB and HDMI and various things. And if you want, in this course, you probably can do all of the homework using a Raspberry Pi if you so desire. So this is what hardware really looks like. It's kind of the inside of something. Normally it's in some kind of case and you don't get to see it. And that's what it looks like. It's kind of got this green and little silver and gold. I think they're very beautiful. They're very pretty. A lot of engineering goes into making these things. And so we kind of have a block diagram of what's going on in here. And there's just some terminology. The brains of it all, well, we draw this block diagram partly because, and here's parts are coming off of this. I don't know what that was. It's okay. It's broken anyways. And if you have a desktop computer, this is more like what it looks like inside. This part is called a motherboard, and it's kind of like the thing that connects and brings everything together. It's got a bunch of wires. Each one of those little lines here is wire. It's covered with sort of a lacquer. And then there are things that penetrate the board and then connect to various chips. And this whole thing is what this picture is, but it really is connecting a number of different components. The central processing unit that I've spoken of before, put that back down, central processing unit is the closest thing a computer has to a brain, but it's barely a brain. It's really just a super fast programmable calculator. We make it flexible by our creativity when we write programs. We make it seem intelligent. It's people that make it intelligent by taking our own knowledge and putting it in. This is not itself intelligent. There's nothing to fear from this. It's just not that smart. So this is the thing that's programmed to ask the question, what's next? And then we have to have a set of instructions that feed this thing really fast, billions of times a second. And that's what this is. This is the random access memory. And we have memory chips, and they're connected together through the motherboard. So we have the main memory, and we have the central processing unit. And this is where our high-speed instructions come from. This is where our high-speed data is stored. And this is the thing that asks what next, and it reads its instructions from here. And you'll see they're kind of like, boop, they're not quite connected together, but eventually they're kind of connected together. Don't feel too bad about this hardware. It's all old, and it's all broken, and it can't be hurt. So the next thing we got is input-output devices. I'll go back to my Raspberry Pi. So the Raspberry Pi has a USB that you can connect a mouse or a keyboard. It has a HDMI that you can connect a monitor to. It has an Ethernet connector. So these are all examples of input-output devices. And then the last thing on the screen is the secondary memory. So this RAM, on the Raspberry Pi, the CPU, the central processing unit, and the RAM are all in this one chip in the middle. It's called SoC, or System on a Chip, where they put more parts there. So in a sense, they've collapsed this and a lot of this all down in the Raspberry Pi to one little guy. But it's still architecturally the same thing. There's a central processing unit, there's main memory, there's graphics cards, etc. So input-output devices. Oh, and this guy has input-output devices too, like USB and keyboard and monitor, etc. So they're very similar. It's just this is new and this is old. Everything gets smaller when it gets newer. Okay. Okay. So the last thing we got to talk about is the secondary memory. Oh. When the power goes off, these things sort of go away. The data in this RAM goes away. It's just designed to be really fast, but not permanent. So we need a place that's permanent. That's what secondary storage is. That's what this secondary storage is for. This is permanent. This is fast, and it cha-cha-cha-cha-cha really fast. And but this is permanent, and this is slower. Okay? So the secondary memory, I've got two kinds of secondary memory. Oh, dropped it on the floor. Two kinds of secondary memory. I'll start with the Raspberry Pi. The secondary memory of the Raspberry Pi is this SD card. It's like a disk drive. It still is permanent, does not require power to maintain its data. The data stays permanent. So in the future we will see more of these flash style drives and SD style drives. So the Raspberry Pi is kind of alluding to the future. There's a disk drive in here. It's not really a disk, it's also flash memory. But in the old days, in the good old days, back when I was a kid, our secondary memory was a disk drive, and it had platters, and it spun, and it made a satisfying noise, and it would move in and out to read data. And I'll show you a video of this just in a bit. And so these would record the data on the magnetic platters, and then when the power is taken off, the data would still be magnetized. And then it would go and move to the right spot, spin it around, and read the data. And again, this is kind of messed up in a pretty bad way. So, there we go. Central processing unit, brains of the operation. Main memory, fast, but goes away when we power off. Input-output devices, keyboards, etc. And then storage that maintains its data across power cycles. Okay, and I just said all that. Okay, so then the question is, where do you belong in this? Where do programs live? Where do we write? And the answer is, we kind of live in the memory, right? What we do is we put our programs into the memory, and then the CPU pulls the programs out of the memory. So we have to write our programs and put them into the memory. When we start them and run them, we're really loading them into the memory so they can be fed rapidly to the CPU. Now, the computers don't really execute Python, like if x less than 3 print, but that's what we tend to want to write, because what the computers really execute is a thing called machine languages, which is a series of zeros and ones that pretty much translate directly to what's on these pins. There's voltages that go up and down. That's called machine language. Source code like Python, is written in a way that's most convenient, well, at least more convenient. Machine language is what's most convenient for the hardware. So we have to translate from source code to machine language, and that's what the Python program does for us. We write in Python, and Python translates to machine language for us. So I got a couple of videos that give you a sense of how this all works. We'll start with CPU. And what this is going to do is this is going to show you the intensity of how much electricity. The thing that gets hot inside your computer is this little guy right here. And we're going to see in this video just how hot it can get. Okay, so welcome back. So the next thing I'm going to show you, I showed you a hard disk that sort of didn't work, but we're actually going to show you a real short video on how a hard disk works, that someone took the cover off and actually applied power to it. You don't want to do this yourself if you have a hard drive. I've read, and some people say that you can do it for a few minutes and then the drive kind of destroys itself if you run it with the cover off. So let's take a look at this. Okay, so that's sentences. Now, paragraphs. Let's talk about paragraphs. Paragraphs are the combination of sentences to make sort of a thought together. Multiple sentences, multiple lines. So the interactive Python that I just showed you is fine for running 1, 2, or 5 or 6 commands. But ultimately, we're going to write much longer bits of Python. And so we write what's called a Python script or a Python program, and we put these in a file. And if you went through the prerequisite, you will have seen me edit in a text editor, save the file, and then run from the Python file. Okay? And so we call these files, put .py on the end of them, py on the end of them, and we're giving Python a script to execute. So, interactive, you're typing directly into Python, and it's doing it right as you're talking. You're still doing it in an order, and the order does matter. In a script, you type it all into a file once and say, Python, do it all. Now, when you write one of these things, there are patterns for combining these. There are things that we do to these lines that sort of treat them differently. It's like a recipe, a set of instructions. Start at the beginning, but it's a little more complex than that. Some steps are just sequential. Some steps might be skipped. Some steps we do multiple times. And other times we have kind of like a set of steps we do over and over again. So here's some pictures. And here's 4 lines of Python, a little simple paragraph. And it's got a sentence that says x equals 2, print x equals x plus 2, which says go grab the old value of x, add 2 to it, stick it back in x, and print x. So the output of this program is 2, then 4. Because x was 2, we printed it, then we added 2 to it, and then we printed it again, so it was 4. Now, these flowcharts, don't worry, I'm not going to make you draw these. I just draw these in case cognitively it makes it easier for you to understand what's going on. So, x equals 1 is the first step. Sequentially, it just continues on. It runs the print. X equals x plus 1 runs the print. So this is just straight through. It'll make more sense when we see a little more convoluted things. So this program just starts naturally. Python starts at the beginning and works its way down through the end. That's sequential stuff. That's the normal order of business. Now, a conditional is a step that may or may not get executed. If all we did was sequential steps, programs would be kind of dull, right? They would just be like, blah, 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 stop. So there's things like, oh, what if you do this or what if you do that? And so we do things like, if you have more than 40 hours, I'm going to pay you a different rate than if I have under 40 hours. Those kinds of things are if, the word if. So in Python, the way we express this is we use the keyword if. So we say x equals 5, and then we say, if x is less than 10, this is a question that's being asked. Is x less than 10 or not? Yes or no? If it is, we execute the indented bit. If it's not, we skip it. In this case, since x is 5, we execute it. And then we come back here, and we're going to do another one. If x is greater than 20, well, this turns out to be false. So we skip that. So bigger does not run. That line never runs. So the output is smaller, fini. Now, here we can take a look at it sort of in the picture diagram. We run x equals 5. We ask a question. This doesn't hurt x to ask the question. Is x less than 10? The answer is yes, so we kind of drive down this little path. We print smaller, and then we rejoin the freeway. Is x less than 20? No, so we skip and we continue. So this never gets executed. So you can think of it either way. You can think of it either sort of like Gestalt, say, if this is true, do what's indented. Or you can imagine sort of a little car driving down a highway, making turn choices as it goes. They're equivalent. Over time, it's probably, you'll just start seeing this and start thinking this way, but sometimes it helps to think about it this way for a little while. Okay. Now, the next thing I want to show you is repeated steps, steps that happen over and over and over again. Okay? And that again, when I said, oh, computers are good at handling a billion words, well, that means it has to have a loop or a repeated section, one for each word. It's going to do something for each word. And so, here we go. And in Python, let's pick a different festive color. Let's pick purple as a festive color. So here's our program. Starts at the beginning, sets the variable n to 5, and then a keyword, reserved word while. While n greater than 0, again, this is asking a question. This is asking a question. Is n greater than 0? That's a question. If yes, we're going to do this. If no, we're going to do that. Over here, if it's true, we're going to execute the indented part and then come back and do it again. If it's false, we're going to skip down. So it's kind of like an if, except it keeps doing it over and over and over again. So it comes in, sets n to 5. Is n greater than 0? Yeah, sure. So we print n, out comes 5. Then it says n equals n minus 1, so n becomes 4. We can change colors. Then it goes back up. Goes back up and asks the question again. N is 4. It's still greater than 0, so it comes through. Prints out 4, subtracts 1, so n is now 3. Goes back up. Is n 0? Is n greater than 0? Yes, it is. Print out 3. Subtract 1. Now it's 2. So out come 3 and 2. Then it goes back up. Still greater than 0? Yes, it is. Print out 2. Or wait. Now it's 1. Now we subtract 1. It becomes 0. Is it greater than 0? No. And we finally leave. And we finally drop down. And so the last thing that comes out is the print of blast off. So this is a loop. The notion that we're going to run this little bit of code 5 times. Excuse me. We're going to run this little bit of code 5 times. And loops have these things we call iteration variables. And that is this n. It's a variable that specifically is changing each time it goes through the loop. And that way we can sort of control the loop. We can decide when it starts and when it stops. We can tell if we're at the beginning or the end, or the first one or the last one. We'll do a lot of stuff with loops. This is an iteration variable because we iterate, repeatedly iterate through the loop. Okay? Any questions? Can't do questions. Okay. So now, if we go back to the little story that you got several chapters to understand. Don't worry. You actually got like through chapter 9. So don't try to understand this program right now. I'm just trying to give you a sense of what the picture is going to be, right? So here are some sequential statements because they aren't indented. Those 5 lines are sequential. They just go one after the other. Then we have 4, and it's indented. This is a loop. This is going to run a bunch of times. Then we're done with that. We do some more sequential stuff. Now we have a for loop, and that's going to run a bunch of times. And then we have an if, which may or may not run. So this little block of code is conditionally executed based on something, and here's the question that we're asking. So that's the question. And then at the end we do a print. Now again, don't try to make too much sense of this. I'm just trying to show you sequential, repeated, repeated, conditional. Okay? Just those concepts show up in pretty much every program that we build. So, let's do a couple more little exercises that get you sort of in the mindset of being a programmer and how programmers tend to have to think about problems a little bit differently. So here we go. I call this an animated short story. And your job, I'm going to give you several sets of numbers, and I want you to find the largest number in the list of numbers. Now, it's not so important to know what the large number is, but also to think about how your mind attacks the problem. What your eyes are doing, what your mind is doing, how you break a bigger problem down into smaller problems, how a human solves this problem. And then we'll focus on how a computer might have to look at the problem differently. Okay? So don't just get the answer. That's not so important. Think about how you get the answer. So don't just scroll ahead in your YouTube and cheat and go get the answer. Think about actually solving the problem and then monitor what your brain is thinking as it goes. So here we go. So I'm going to give you a list of numbers, and you are to tell me what the largest number is. Ready, set, go. I didn't make it easy. You're looking for the largest number. Did you get it? Did you get it? Did you have to go back a couple of times? Actually, I don't care what the answer is. The question is, how was your brain solving? Okay, you probably want to know what it is. The answer is 198. That was the largest number. Of course, what I was doing is I was moving it to make it difficult. But here's the thing. How do humans look at this? Do humans did you look at 25, then you looked at 1, then you looked at 114, and did you just look at them slowly one at a time like this? Or no? I doubt it. If you are, maybe you're a computer. Maybe I'm talking to computers. Maybe you're all computers. I'm certainly not a computer. Maybe you're all computers. Okay, enough of that. No, that's probably not how you did it. What you probably did was you had your eyes move around the whole thing very rapidly, and the first thing that you figured out is that there were one-digit blobs, there were small, medium, and large blobs of purple. And the first thing you knew right away was there was no point at looking at any of the small blobs. Your brain just threw the blobs away really quick. Then you say, okay, given that there's no 4-digit numbers, they're 3-digit numbers. Then what you probably did is you started looking for the first digit. You say, look, there's some 1s. Is there any 2s? Quickly you decided there are no 2s. So you knew that you had to look for the big blobs, and the second digit was probably the thing that mattered. Then you start getting to the 9. You say, okay, there's some 9s. So that means it's 19 something. Then that was the part that you probably had to go check to find the, where the heck was the 190? Oh, 198 right there. Yeah, color-coded. I couldn't even see it. Okay? But the point is humans are great at eliminating sort of bad solutions really fast. And you probably looked at how much purple was on the screen, eliminating the areas that were less purple because you knew that your brain quickly and instinctively knew that the more purple meant a larger number. Computers don't do any of that. They don't do any of that. So, in order to make you feel a little more like a computer, I have another test. And again, the goal is not just to find the largest number, but to monitor as you go what your brain is thinking while you're doing this. Okay? You get it? How are you attacking the problem? What is your feeling as you're attacking the problem? Are you a computer or not? Here we go. I'm only going to give you a few seconds. So, what did you get? My guess is that most of you just said, I don't care. This is such a hard problem. It's a stupid problem, or I'll try to turn my head upside down, or something. It's a really hard problem. The other one was kind of easy. Not that you might not have got it, but you had this natural instinct that allowed you to approach the problem. Okay, I'll show you what the right answer is. The right answer is right there. It is 197. Yay. Right? You can't even if I tell you, it's, there you are. What is this? Is this 500 or 200? Actually, the only way I can do this is I flip it to find it. I mean, it's just not what humans are good at. This is a little bit more like how computers see the world. But the fact that the data is frontwards or backwards should sort of make no difference, right? Computers need a strategy. We need to give them a strategy. Okay. So here we go. One last experiment. Now, I'm going to show you numbers one at a time. And at the end, I want you to tell me what the largest number that you saw was. Ready? Here we go. First number. What was the largest number? As a matter of fact, how did you solve that problem? You solved that problem most likely because you couldn't look at all the numbers at the same time, so you probably created a variable in your head without even knowing it. And you put into that variable, you called the variable the largest number I've seen so far. And you hadn't seen any, so let's say the largest number you've seen so far is -1. Then I showed you 3. And you said to yourself, well, -1 is no longer the largest number I've seen, so I'm going to keep that one. I'll keep 3. That's the largest I've seen so far. And now I see 41. 41 is larger than 3, so I will keep that. And now I see 12. Now 12 is crap because it's nowhere near as good as 41, so I'm keeping 41. 74. Oh, 9. 9, not nearly as good as 41, so I'm going to throw that one away. 74, better, keep it. Keep that one. So I'll keep 74. And the last number is 15. Don't even know it's the last number, but we don't want to keep that one. And so now we're done. And so we know that at the end, what was during the loop the largest so far is the actual largest of all the numbers. And we don't remember exactly how many numbers there were. So that's kind of like thinking like a program. You have this kind of sliding window. It didn't matter if I gave you 1 billion numbers or 5 numbers. I think there were 5 numbers, actually. This notion of the largest so far is a powerful notion. As a matter of fact, it's central to the program I've been showing you. Now, I don't want you to try to understand this, but this part in the purple, is really saying, I'm going to loop through the counts of all the words. So it's got a word like the is 15 times and clown is 4 times, and it's going to look through all the pairs of word value combinations. And it's going to basically say, I'm going to go through the counts that I have, and I'm going to check to see if the count I'm looking at is bigger than the biggest count I've seen so far, and if it is, I'm going to remember it. Now, don't worry about this. We haven't even covered any of this stuff. That's what chapter 2, 3, 4, 5, 6. But this is an algorithm, a paragraph, a pattern that allows you to find the largest number. And we'll look at this again in great detail in upcoming chapters. So this is kind of thinking like a computer, having a sliding window across a long list of numbers and coming up with something that is the answer that you need. Okay, so that's the end of this lecture. Read chapter 1, write your Hello World program. Make sure if you haven't, get Python installed. As you read this chapter, and even as you install Python, and even as you write the first program, don't get too stuck on the details. I was confused for like 8 weeks, or probably 6 weeks in my first programming class. You'll be confused too. Just sort of wander through with me. Keep at it. It will start making sense at some point that's up to you. I can't tell you when it's going to make sense. So don't sort of stare at everything until you get it. Just kind of keep digging in and keep understanding and keep playing, and sooner or later this will make a lot of sense to you. I promise you. See you next lecture. Hello and welcome to Chapter 2. Hope you enjoyed Chapter 1. It was one of the longer lectures, trying to motivate you a little bit. And now we're going to kind of go back to the basics. The Chapter 1 covered sort of the first 4 to 5 chapters of the book. So, as always, this video, these slides are copyright Creative Commons attribution, as well as the audio. And so, now we're going to talk about sort of the really low-level things that make up the Python language. Constants. So, some of this is terminology just so I can say the word constant and you won't freak out. Constant is, as contrasted with something that changes, is variable. We'll talk about variables in the next slide, but for now, constants. Constants are in things that are sort of natural and instinctive, things like numbers, 123, 98.6, or hello world. And so in what I'm doing here is we're using the Python interpreter, and that's how you can tell the chevron prompt. And I'm saying print 123, and then Python responds with 123, print 98.6, Python responds with 98.6, and print single quote hello world single quote. So the constants are the 123, 98.6, and quote hello world quote. So these are things we can use either single quotes or double quotes to make strings. And so programs kind of work with numbers and work with strings, and we have these non-varying values that we call constants. So the other side of the picture is the variable. And the way I like to characterize a variable is it's a place in the memory of the computer. We give it a name as a programmer. We pick the variable name. In this I'm saying x equals 12.2 and y equals 14. I am choosing the name and I'm choosing what to put in there. This is a statement called an assignment statement. And the way to think of the assignment statement is that it sort of has a direction. We're saying, dear Python, go find some memory. I will use the label x later to refer to that memory, and take the number 12.2 and stick it into x. Then this is sequential code. Then the next thing I want you to do is I'd like you to go find some more memory, call it y. I will call it y later, and stick 14 in there. Okay, and so that ends up sort of with two little areas of memory. You know, one labeled x, and here's a little cell in which we'd like a drawer or something, and one labeled y, and we have 12.2 after these lines run. We have 12.2 in one and 14 in the other. Then, for example, if there's another line that's down here, so there's this third line after this has happened, x equals 100. Remember, this has kind of got a direction to it. Say, oh, remember that x that I had? You know, I would like now to put 100 in that. So as I'm thinking this through, I think of that as sort of removing the 12.2 or overwriting the 12.2 and putting 100 in its place. And so at the end here, x is left with 100 and y is left with 14. So these variables can kind of have one value in them, but we can look at them and we can reuse them and put different values in if we want. There's some rules for naming your variables. Again, you get to pick the variable names. Often we pick variables that make some sense. We'll talk about that in a second. In Python, variables can start with an underscore. We tend not to, as normal programmers, use those. We let libraries use those. It has to have letters, numbers, and underscores, and start with a letter or an underscore. Case matters. So spam is good, eggs is good, spam 23 is good because the number is not the first character. Underscore speed, that's also perfectly fine because it starts with an underscore or a letter. 23 spam starts with a letter, starts with a number, so that's bad. This starts with something other than a letter or a underscore, and you can't use dot in the variable name. It turns out the dot has meaning to Python that would confuse it. And wouldn't understand what we really mean there, and so that would be a syntax error. Because case is sensitive, that means that things like all lowercase spam is different than uppercase s and all uppercase. These are three distinct variables that are unique. Most people don't choose variables that might be so confusing. So this, to you as you write it and as to anybody that might read it, would find three variables named as very confusing. So it's a bad idea. Don't do it. But I'm just showing you as an example that case can make a variable name distinct. And again, this variable is a place in memory that we are going to store and retrieve information, whether that be numbers or strings or whatever. These are things that we control. Now, Python also has a set of reserved words, and what it really means is you can't use these for variables. These words have very special meaning, and, for, is, raise, if. So you can't make a variable named if. It'll be like, oh no, that is if. I know what if is. And so these are words that Python has as its core vocabulary and forbids you to use them for other purposes like variable names or later function names. So that's kind of the vocabulary: constants, variables, and reserved words. Now, we take these and we start assembling them into sort of sentences, statements, Python statements that do something. So we've already talked about an assignment statement. It has kind of an arrow here. It says, hey, Python, go find me a place called X. Take the number 2 and stick it in there for later. Then continue on. Now, because there's an arrow, the right side of this is done first. And so so this right side, you can kind of ignore for the moment the left-hand side, and it calculates the right-hand side by looking at the current value for X, which happens to be 2. Then it adds these two things together and then gets 4. And then at the point where it knows 4, that this number is 4, it will then store that back into X. And so then later we print X and we will get the 4. And so again, this is a sequence of steps, and the variable X changes as these steps continue. And when we're saying print X, that really means print the current value for X. So we can do a number of different operators in assignment statements. We calculate this right-hand side. This is sort of all calculated, whatever this is, based on the current value for X, does this calculation. And then when it knows what the answer is, it assigns that into the variable that's on the left-hand side of the assignment statement. Again, calculate the right-hand side completely and then move it to the left-hand side. Some early languages actually didn't use the equal sign for the assignment operator, this assignment operator, and in a way it kind of, get a good color here. Some languages, an early language, actually used an arrow. Arrows aren't really on people's keyboards. Another language used colon equals as this assignment operator, but we use equals. Now, if you're familiar with math, this can be a little confusing, like x equals 1, and then x equals 2. That, as mathematics, would be bad math, because in a proof for a problem, x can only have one value. But in programming, if this was two statements, that means just x had a value, and then the value for x changed later. Okay, so just kind of go through this. Because it's working from the right-hand side to the left-hand side on assignment statements, it is pulling out these x values. So x may have 0.6. It pulls the values out before it's sort of ignoring this part right here, and it's just going to try to resolve this expression. And it has multiplication in parentheses and things like that. So it basically pulls the 0.6 into the calculation, does the 1 minus x, which gives you 0.4. Then it multiplies these three things together, giving 0.93. And then when it is all done with all of that, it takes that 0.93 and then puts it back into x. And so this is just sort of emphasizing how the right-hand side is computed to produce a value, then it is moved into the variable, and that is why you can have sort of x on both sides, because this is like the old and this is the new. This is the old x participates in the calculation, and then when the calculation is done, it becomes the new x. Hope that makes sense. So this on the right hand side here is a numeric expression. So we have a number of different operators. Some of them are instinctive, intuitive, the plus and the minus. The reason some of these are so weird is in the really old days we didn't have too many things on the keyboard, and a lot of programs were very mathematical. And so they figured out what was on the keyboard of the computer equipment of the day, and then they had to fake certain things. So it turns out that plus and minus were on the keyboard, and so plus and minus are addition and subtraction respectively. There was no kind of times operator for multiplication, and dot was used for decimal points, so they used asterisk for multiplication. So in computers, languages, nearly all of them, they basically use times for multiplication. Slash is used for division, so we say like 8/2, which is 8 divided by 2. Raising something to the power, like 4 squared, that is double asterisk. And then remainder is if you do a division, that gives you the remainder rather than the divisor. So 8/2 is 4, remainder 0. So the remainder is what you get with this particular operator. There's a few cool things that we can do with remainder that we won't talk about right away, but it's there. And so here's just a couple of sample expressions. Let's give me green. Okay. So again, I'm using the Python interpreter, so you can kind of it's just the prompt. These chevrons are the prompt. Create the variable xx and assign it to 2. Retrieve the old value in an addition, then print it out and put it back into xx, so xx has 4. Yy, this is a multiplication. 440 times 12 is 5,280. Yy over 1,000. Now this is a little counterintuitive. Because yy is an integer, it then does it in a truncated division, and so 5,280 divided by 1,000 is 5. Now, so that's an integer division. We'll see in a second about floating point division. Now we take the variable jj and we set it to 23, and now we're going to use the modulo or remainder operator to say what is jj. What is the remainder when we divide this jj by 5? And so if you think about this, we take old long division, 23 divided by 5, you end up with 4, and then remainder 3. The modulo operator, or the percent, or the remainder operator, gives us back this number, and so that's why kk is 3. It is the remainder of 23 when divided by 5, or the remainder of the division of 5 into 23. And the raising to the power, 4 cubed, no, that's not so nice, 4 cubed is 4 star 3, and so that ends up being 64. So that's just operations. Now, just like in algebra and mathematics, we have rules about which operations happen first. In general, things like the power happens before the multiplication and division, and then the addition and subtraction happen. And so there are some rules that when you're looking at an expression and trying to calculate what its value is, if you don't have parentheses, it follows these rules. And so the rule that sort of trumps all the rules is that parentheses are always respected. So a lot of us just write these with parentheses in place, even sometimes though you don't need it. Then after parentheses have been handled, then it does exponentiation. Then it does multiplication, division, and remainder. And then it does addition and subtraction. And then when all else being equal, it just works left to right. So let's look through an example. So here is a calculation that is, 1 plus 2 times 3 divided by 4 over 5. And the question is, what order does this happen? Okay. And so let's sort of take a look at this. And so we start with, are there any parentheses? And the answer is no, there are no parentheses. So let's go next. Power. And so the power says, okay, let's look across and find those things that are raised to a power, and the 2 cubed, or 2 to the third power, is the power. So we're going to do that one. Okay, and then we can, the way I do it when I'm sort of doing these slowly is I rewrite it. So the 2 to the third power becomes 8, so it's 1 plus 8 over 4 times 5. And then now we can say, oh, power, that's taken care of. Now we're going to do multiplication and division, and we go across. Now we have both a division and a multiplication. Okay, and multiplication and division are done at the same time. So that means we do left to right, which means we do the first one that we encounter first. And so that will be 8 over 4 because of the left to right rule. And so we find that one, and that's the one that gets computed next, and that turns into 2. And again, I like to rewrite these expressions just to keep my brain really, really clear. After a while, you just do it in your head. But I rewrite them when I was first learning it. At least I rewrote it all the time. And so next, looking at this, there's a multiplication. We're not done with multiplication yet. So the 2 over 5 is the next thing. And then we do that calculation, and that becomes 10. And again, we rewrite it. And now we've done the multiplication. And we're going to do addition next, and that's just 1 over 10. And that becomes 11. And so basically, this big long thing, through a series of successive steps, becomes 11. And indeed, when we print it out, that's what we get. Okay? So there's the rules that are parentheses, power, multiplication, addition, and then left to right. But smart people usually just put parentheses in. You know, so here's an exam. Oop, go back. Here's an exam question. Now, I wouldn't write this code, right? I wouldn't write this code this way. I would put a parenthesis here and a parenthesis there. It's the same thing, because that's exactly, the 2 times 3 is going to happen, and the 4 over 5 is going to happen, and then the plus and the minus will happen left to right. But why not make it easier on your readers and just put the parentheses in? Because they're redundant, they're not necessary, but away you go. Now, if you don't want it to happen in that order, of course, then you have to put parentheses. If you want the addition to happen before the multiplication, then you have to put parentheses in, which you can. But we tend to recommend that you use more parentheses rather than less parentheses. Now, Python integer division in Python 2, which we are using Python 2 for this class. There's a new Python 3 that the world is slowly transitioning to, and a lot of people are using it and teaching, but it's not as common sort of in the real world with libraries and utilities. And so we'll stick with Python 2 for a few more years until Python 3 really kind of turns the corner. It's nice to have it there, but there's so much Python, and it's so popular, Python 2, that it's just kind of hard to get everybody up to Python 3. So in Python 2, integer division truncates, and you saw that before, where I did the 5,280 by 1,000, and I got 5 as it. But we can look at a couple of examples that make this really quite clear. So 10 divided by 2 is 5, as you would expect. 9 divided by 2 is 4. Not exactly what you'd expect. You kind of expect that to be 4.5 instead of 4. But in Python 3, it will be 4.5. But for now, in Python 2, 9 over 2 is 4. And 99 over 100 is 0. Now that seems rather counterintuitive, but it is a truncating division. It's not a rounding division. It's a truncating division. Now, interestingly, if you make either of these numbers have a decimal, make them what we call floating point numbers, then the division is done in floating point. So 10.0 over 2.0 is 5.0. Now, these are different. This is an integer number, and this is a floating point number. It's 5.0. And then 99.0 over 100.0 is exactly as you would expect, and it's a floating point number. So now you can also mix integers and floating point numbers as you go. So here we have 99 over 100. Those are both integers, integer, integer. And that comes out with 0 because it's truncating. Now if we have an integer and a floating point number, 99 over 100.0, then that comes out as 0.99. And either one, if we have 99 over 100, that's a floating point and that's an integer, we still end up with a floating point. So this is a floating point, floating point. And even in complex expressions, as it evaluates, when it sees an integer, so the first thing it would evaluate is this would become a 6. So it would be 1 plus 6 over 4.0 minus 5. Then it would be doing this 6 over 4.0, and that would be 1.5. 1 plus 1.5 minus 5. And so this is an integer, and that's a floating point, and the result becomes a floating point. And then the rest of the calculation is done floating point to the point where the ultimate is a floating point negative 2.5. So you can throw a floating point into a calculation, and as soon as the calculation touches the floating point, the remainder of the calculation is done in floating point. Kind of converts it to floating point, but it doesn't want to convert it back because it considers floating point sort of the more general of the representations.